Good evening, everyone. The House of Sultan Chand and Sons Private Limited and Method AI welcome you once again to today's Artificial Intelligence webinar. It's nice to have you all here, and we thank you for that. A bit about the House of Sultan Chand and Sons Private Limited first. Pioneers in the field of book publishing in post-independent India, we cater to students from pre-primary to university level, churning out over 600 titles, besides adding new ones to our stable year after year. Known for competently written, elegantly produced, and reasonably priced books, our publications are widely prescribed in reputed schools and colleges across the country, as well as in some neighboring nations also. Our authors are distinguished academicians, professors, and educationists with vast experience and expertise. We are proud to be associated with them. I now introduce you to the host of today's webinar, Dr. Sachin Gupta, author of the hugely popular Artificial Intelligence textbooks for classes 9 to 12 and Data Science books for classes 9 and 10. Dr. Gupta is Dean Research and Innovation, Maharaja Agrasen Institute of Technology, Guru Gobind Singh Indraprastha University, Delhi. It's a matter of pride for us that Dr. Gupta's book on AI, Decoding Artificial Intelligence, has won the Outstanding Contribution to AI Literature Award. Besides, Dr. Gupta has also been HOD Computer Science Engineering and MCA Department, Dronacharya Group of Institutions, Deputy Director and Head, Computer Science Department, Chandraprabhu Jain College of Higher Studies, affiliated to GGSIPU, Delhi. With a teaching experience of over 23 years, which includes teaching undergraduate and postgraduate students and researchers, Dr. Gupta's academic pursuits have been fairly meritorious, winning him several awards, distinctions, scholarships, including the Certificate of Academic Excellence by GGSIPU. Dr. Gupta has also contributed to various journals, conferences, and books for schools and higher education, both nationally and internationally. His achievements are truly commendable. I now invite the man himself to take you through today's session, Dr. Sachin Gupta. Thank you.
Thank you so much, sir. Thank you so much to everyone who has joined the session today. So this was again on demand that we wanted to have computer vision, how machines see. I believe all of you are already reading the book that we have, but I wanted to make this more like a exploratory discovery type of presentation or seminar where everybody would be able to ask whatever kind of doubts that we have in teaching that. So I'm making it fairly comprehensive, technical for that matter. So bear with me if there is any concept that you feel is a little hard, but it is meant to be because we are now dealing with class 12. So there will be a lot of technical details which we have to bring to our students. So that is basically the purpose why we are having this in a very good detail here. So I hope my screen is visible. Yeah,
Yes, it is.
yeah. So we will talk about the evolution. Yes. Okay. We'll talk about the evolution of computer vision. First thing first, computer vision is artificial intelligence in one form that we allow the computers to get some data, process that data, and eventually get intelligence from whatever we process. But here, whatever data that we'll talk about would be in the form of digital images, it can be videos, anything which a computer can see would be used to process computer vision. Naturally, what we are going to be dealing with is that where does the input come from? Is my input coming from a static image? Is my input coming from a camera, sensor? It is something in the form of a map, anything which we can see, visualize, any graph that we upload. all of that can contribute to computer vision. Even if opening my camera right now in the laptop, that is how is the filter behind me is being made to work. That is again a computer vision technology. So this basically is all computer vision. Now everything in this format would start from a pixel. So a pixel would be the smallest controllable element of a picture represented on the screen. If my complete screen is horizontally and vertically divided into parts or the smallest fragments, I would call each one of them as a pixel. So a colored image would be represented as a red, green, and blue, three channels. A grayscale image, on the other hand, would be represented by shades of white to black. Right? And how a machine sees it is it would be looking at it in the form of only numbers. It does not see it in the form of uh, any colors or any information at all. It just sees it in the form of a number. Again, the quality and detail of images are directly related to the number of pixels. So this you would talk about in your digital cameras also. When I say my image is a couple of megapixels, that means that is the total number of pixels in it. For an image which is low resolution, the storage requirements are less, but the quality, you can't zoom it. It gets what we say, it gets pixelated when you stretch it. On the other hand, when I have a high resolution image, you can keep on zooming in it and it would still be able to maintain the same quality as it had earlier. So that is what we talk about in the terms of pixels. A higher pixel count has over 2 million pixels in a 1920 cross 1080 image. That means it has higher resolution and more detail. So one quick question to all of you, and I would like you to talk in the chat box. If I am doing computer vision, would I prefer a very high resolution image or low resolution image is preferable? This you can answer in the chat box quickly. Okay. One says hi. Go on, make an answer fast because this is essential. Okay. So we have a consensus here that we require a high resolution image on anybody for low resolution. Perfect. So this is as good as it gets. What if I tell you no, computer vision would always try to work with a lower resolution? That is the what we will come to this. We will certainly not use a high resolution image, and we'll see the reason why. So digital images are represented in a 2D or a 3D for video or volumetric data. Grayscale images, single numerical value 0 to 255. So intensity from black to white. Color images, each pixel has three values, 0 to 255 on red, green, and blue. This is again oversimplification. I'll come to. Yes, Anjeev, thank you so much for having that. So, how do our images form is one basic fundamental that the more information I want to capture in an image, the higher information I would to keep in per pixel. So earlier we used to have images which were simply bitmaps. You would have a 0 or a 1, simplifying it's a black or a white pixel. Then started grayscale. We wanted to add more shades of gray. From bitmap, we went to images where there were 8 bits per pixel. So from 0 to 255, the 8 bits would take a value for each pixel. And between 0 to 255, whatever intensity that we wanted to portray, we would have one value selected. So now we had 256 different shades of gray. But we wanted more. We wanted a color image. So we wanted that let there be red represented between 0 to 255. So 256 values of red, 256 values of blue, and 256 values of green. And we will mix them in a certain manner so that we can produce all different colors. But if I have three channels, what would be the size of each pixel if each color is taking 8 bits? So we would now have 8 bits for red plus 8 for green plus 8 for blue. Correct? Three channels, 3 bytes. Correct, absolutely. That means 24-bit. So my image suddenly size increases because for each pixel, we are now having instead of 8 bits, 24 bits. And mind you, we are not adding yet what is the texture. That is again another additional information that we can add because gradient or smoothness that can be added by a texture. So in modern cameras, the pixels may be 32 bits per pixel also is not very uncommon. So our images may go even to that extent that per pixel, how much information are we storing? That would depend on how much information do we want to represent in an image that is going into the digital. Yet another thing, if you are already teaching computer vision, you would have seen programs where we try to change the number of channels to 3 to 1. That means we always try to convert a RGB image into a grayscale before we want to go into uh, applying computer vision to it. Correct? There are several programs that you would find that where we convert the color image first into grayscale because the primary reason is all machine learning is data intensive, but it is also computation intensive. So if I am processing any image with a large amount of bits, the more the number of bits, the more the computation my algorithm has to do. And with images comes automatically the data is very high. So as we just saw that an image with this resolution has over 2 million pixels. Okay. Can somebody guess how many, if I have got this many number of pixels, I'm just posting it into the chat window. How many features are we going to have in that image? Just take a rough idea. Because when we are doing housing prices, we have got 8, 10 or 15 features. When we are doing some other text-based analysis, we have certain number of features. When we are doing some neural network, we again work with features because features are the one which we are going to extract. How many features do you think would be there in the image if it has this resolution? Take a wild guess. 100 in the range of thousands or in the range of hundreds or less. You can open your mic and speak also. I don't mind that. So we are getting 1,000 features, 2,000 features, couple of thousand, correct? Any more? This is the total number of features if we are talking about that 1,000 is a very big number when it comes to features. But the number of features here are that is the surprising part. Every pixel is a feature when we are talking of computer vision. Sometimes we would club them together to reduce the number of features that we want to work. Sometimes we would ignore certain pixels, or sometimes we would reduce the number of information, additional information within a pixel. So we can't say that features would be counted by how much do we see. That is the basic difference. So when I see some images on my screen now, some photographs, some people who have their, I see letters, I see Karishma having a very beautiful background put in the pixels. So from us, we would be able to count maybe 15, 20, 100, 200 features. Yet this is something that we can pick out. But for a computer, it would be seeing everything, every pixel as a feature. So this is one primary reason why we reduce color images to RGB from RGB to grayscale to make sure we will do that. We will do that. So from RGB to grayscale is done to make sure that the information contained in the image is reduced because we do not want our algorithm to be overwhelmed with data. We want some less amount of data to work with. Right? This is also true for when you see teachable machine. I hope this is still visible and you get started. So if you open a image project in teachable machine, this talks about that I would want a 224 cross 224 pixel color images. It doesn't work with higher resolution, right? But it also gives you a 96 cross 96 pixel grayscale images for embedded image model. Now let us understand what does it mean. That for a color picture, the teachable machine, because it is computing everything within the browser, the amount of computation power that we have is limited. So teachable machine would be able to take images which are 224 cross 224 pixel if it runs on the web. So it is still having a lot of features, but we are not capable of processing beyond that. So if I give it a larger, higher resolution image, it would not be able to process. Whatever images we upload, it converts internally all of those images to 224 cross 224 pixels. But what if it was supposed to run on my mobile phone? So to run it on a mobile phone, we would have a different model, which is an embedded image model, or to run it on a Raspberry Pi or any microcontroller. We want the image resolution to be even lower. We want 96 cross 96 pixels because there my model is supposed to be smaller in size. It cannot process anything higher than that. So when we are trying to work with images, we have to be very careful that what size or what resolution are we using. Yeah. Okay. So let's go ahead of this. So the early evolution of how machines were able to see. Initially, the first digital image was created by Russell Kirsch in 1957. He scanned a black and white photograph of his son. It was a grainy 176 cross 176 pixel image. This was the first digital image. But after this, we were working this for satellite imagery, medical scans, X-rays, MRIs. For all of them, we required digital images. Initial efforts in the imaging that we would not talk about pixels completely. We would simply talk about algorithms which were talking of edge detection. And this is true today also. So for an input image, we would do some pre-processing, some feature extraction, and after extracting the feature, we would be able to classify. So we just had a question. Can you cite some features available in this picture? So for this, our feature extraction algorithm might take one feature as this, the other as this, the third as this. But all of these are internally represented as pixels. When I'm clubbing those pixels together into one feature, that is giving us a higher level abstraction of what my feature may look like. Correct? So breaking up an image into pixels is the job which a digital image does. But combining those pixels into one edge, which might, or into a circle, or into an eyelash, or into something that we can recognize, because we can't recognize pixels. We as humans recognize a wheel, we as humans recognize chassis or the front part of a motorcycle, anything that we can recognize. But computer recognizes only pixels, right? So this is what it is going to recognize as a feature. So for the feature extraction, which parts have certain shape which can be clubbed together, and what part would I be able to uh, easily understand from the perspective of a human being, is our way of doing it. So this is a oversimplified representation. For a computer vision algorithm, this might not be completely true. It might actually be looking at a completely different set of features at all, right? We will see one specific example where we can check out the features when we do computer vision in detail right now. But for the time being, the higher the resolution of an image, the harder it would be to process in deep learning. There is not just one image. When we are deep learning, we are running a lot of images to learn from. So for a recognition of a cat, we are feeding it 50 or 100 cat images. If each one of them is high resolution, the system might not even be able to process it without a GPU. And sometimes even the GPU might take multiple days to process that computer vision task that we are trying to work with. So far, so good. Any more questions? Yeah, man. Thank you. So, what happened with computer vision? Why did it come into so much limelight? It was after neural networks emerged. This was the one significant breakthrough because in 1980s came the Hooke transform. It was a mathematical algorithm for detecting complex shapes like lines and circles, even when they were partially obscured. So instead of taking a pixel as a unit, we now try to think of applying a Hughes transform. Let us find which lines are available. So if I have to identify a digit, for instance, I can represent the digit 1 as there may be a slanting line, small slant line, a straight line, a sleeping line, and all of this put together, these three features may be able to identify, yes, this might be the digit 1. So for digit 0, there may be multiple single lines which are together in different orientation. But yes, this might be another way of representing a 0 with multiple features in the form of lines, or representing circles with lines by breaking that into very, very small lines. So all of you know that if we have to represent a polygon, from triangle to square, from square to pentagon, from pentagon to a hexagon, decagon, the more number of edges you keep on adding, the more it gets closer to a circle. So that is how that we can say that if we add enough number of lines, we would be able to create a circle-like shape. But see the hierarchy of representing images here, the circle itself is can be broken up into multiple small lines, where each of the multiple small lines can be broken into a large number of small set of images or pixels. So that is how I'm deriving the pixel as a feature, to line as a feature, to circle as a feature. That is how the complexity grows. So for each of the image, the task of the computer vision is to learn the complexity at the higher level and try to understand it at the lower level also. So that is basically what we try to find as features. Then came in convolutional neural networks after the basic neural network. Now CNNs have been around for typically image processing only. So they are a class of deep neural networks which are specifically designed to process pixel data and highly effective for tasks such as image recognition, object detection, or image segmentation. Now, these are different tasks. How do I identify one? What is there in the image or recognizing an image? how do I identify that which object, where is the object available in the image, and how do I break it into parts. This all we would be again discussing. But come to my first question, when I say that how many features are there in the image, now think of the input layer in a typical CNN architecture. The features which CNN sees at the input layer is raw pixels. The higher the resolution of my image, the higher the number of neurons required at the input layer of my CNN network. And the more the number of input images at my CNN network, accordingly, each of the next hidden layer would have a little less, but there still would be very large number of pixels in the next. So we want to reduce this input. So instead of RGB 3 channels, we just uh, compressed it into 8 bits only grayscale. Even from that, we are trying to now have a lower resolution image which would have lesser number of pixels because I might still be able to get intelligence from that. Why this works? I wouldn't require to have a very high resolution image to be looked at by a computer to detect that yes, there is a fracture here in the bone. To the human eye, we require more accuracy. To a computer, because it is dealing with the pixels, it may be able to extract the same information from a little lower resolution image also. That is something that we are counting on. So going on from the input layer, we go to convolutional layer. We will see this layer in. So we create a feature map using some filters. So we try to detect edges or textures and we produce a feature map. Then there is the activation layer, there is a pooling layer, there is a fully connected layer, there is an output layer, and this is something like looks like the architecture of CNN. So for an image, if the image is 224 cross 224, right, we would have a convolution one layer which would be processing all of these images one by one, right? Can somebody, do you think the convolution process is, uh, how does it happen? Is it parallel? It is sequential? I mean, if I have to trace this particular screen from one edge to the other edge, capturing the information in each part of the image one by one, then the next line, then the third next line, then the fourth next line. So for my screen, now Manmohan Malik sir would be the first image portion that I capture. Mine would be second, Gurpreet would be third, Debjani would be fourth, Sandeep Gaur would be fifth. Then I come to the next line, Vinay, Samson, Anjeev, likewise. Okay. Yes, this is a metric. So convolution does what? It does not read one pixel at a time. It would read a group of pixels in the form of a matrix at a time. And it would apply a convolution operation or a filter or a kernel which would try to identify what information can I capture from this block. Then moves on to the next. What information can I capture from this block? Again, it has to check that from the first to the second block, is the feature continuing? Because if it's a line which is spanning across three of these, then obviously that line would be contained in all three times I capture this. This is something when Narendra asked Narendra that what would be the block size. This depends on how much information are we trying to capture. That are we trying to, okay, I'll give you one example here. Please try to understand. If I have to identify a parrot from an elephant, I can keep a very high block size that I don't need to capture much detail because the features of parrot would be very easy to identify versus the features of an elephant. Correct? Because the features are so entirely different. I am doing less task. Now I'm trying to classify a parrot from a crow. Both of them have several similar features. There is a beak, there is the shape is similar, then there are two small legs. I need to capture more information for classifying them. So, but there is a good thing that the parrot is green, the crow may be black. So that becomes a easier classification for my computer vision model. It would still be able to do that thing, but it can still do with a bigger block because the features it is capturing, the feature map, the texture, the color is the identifying or distinguishing thing. What happens when I'm trying to differentiate a parrot from a parakeet? Both green, both have similar body structure, one has a longer tail, but by and large, now I need more features. Now I need to have a smaller field. The block size would be smaller because I need to capture even more detail before I would be able to distinguish between them. We will decide the block size for just give me some minute. So finally, if I am classifying between dogs and cats, my filter size can be block size can be big. But if I am distinguishing between faces of two human beings, because the features are all the same, there is a nose, there are eyes, there is a lip, there. This I can easily figure out. But recognizing one person from the other person where two may be very distinguishing similar, how do I distinguish between them? I would have to now go to for a very smaller filter. So accordingly, I would be able to run a classification like a cat and dog using machine learning. I don't might need to even use a deep learning at all. But when I have to do a human facial recognition, I certainly have to apply deep learning because my filter size becomes very small and then I have to capture a lot of imagery. Are you with me so far? This is easy to understand. No worries. Perfect. So who identifies the block size is another thing that when I am designing this, some of the CNN architectures are pre-decided that give it an image of this size of input, it would automatically have this as a architecture. So it would process every image with this, irrespective of whatever image we throw at it. But if we are creating some custom task, we decide what would be the size of convolutional layer 1. We decide what is the size of con 2. We decide what is the size of con 3. So if you would look at let us look at some example for CNN and check the core. Let us write this in Colab. Let us create a new notebook. And we would be writing this code. Just a minute. So I'll generate with AI. So you will see that when somebody would write this is usually the way a CNN model would be defined. You would be defining that the first layer is a convolution 2D, a 32 cross 3 cross 3, where the input shape is 28 cross 28 cross 1. Then we have a max pooling layer, then we have a convolutional second layer, then we have a convolutional layer third, then we have a dense layer. So this is something, think of this particular code and think of the VGG that we just saw as the same. Instead of the convolution with VGG 16, where we had a 224 cross 224 cross 64, now this, because we are going to run it across a CPU maybe, it takes a very small convolution layer with the what are we going to use the strides or the filters again. So I hope that basically answers the question that you are asking. We decide the block size depending on, we decide what is the kernel, we decide initially that, but after that what happens, that which features are going to be extracted, what features are available, nothing is in our control now. After we give it to deep learning, the basic fundamental difference between machine learning and deep learning is, in machine learning, in the housing prices, we decided what features are we going to learn from. In machine learning, if we were talking about that whether to go out to play or not, we decided what features are we going to work with. But when I'm actually working with an image model which has to identify what is there in the image, I don't decide what features are there. The computer, the deep neural network automatically tries to extract which images are there. It would not ask you which images do you want, which edges do you want to see, or which color textures or anything that you want to see. It doesn't even ask us. It says, give me a structured layered model. I will be the judge of which images are important or which features are important. You don't have to worry about it. And I'm not even going to tell you that what features did I pick. So I'm just going to give you a classification. You feed your image, I'll give it to my black box. My black box is going to learn which features are important, which features are related, what features are common in this image and that. And after that, I will just give you a classification. So you give me any new image. After I have learned which features were important, I will see are these features here available or not. And after having seen that, I will decide which class does it goes to. That happens in a deep neural network where it's a black box. We don't see what happens inside a deep neural network. How can it distinguish one human from the other? We have no idea, absolutely. So that is the kind of, so we can decide what is the neural network like. Based on how complicated our images are, we would decide the, or how much features do we want to extract. That would decide what is the block size. So your student don't need to actually get into that detail for any point of time. Okay. So let us go back to our presentation again. So features, as we talk about, what does it learn? The early layers learn the basic low-level features like edges, corners, and simple color blobs. So this was something that Vijayalakshmi added, that this is the features that we, if I am correct. Okay, YouTube says, sir, can we implement these topics for students? Yes, we can, practically, certainly. So yes, Vijayalakshmi said that edges and blobs are the earliest layer. Corners, edges, blobs are the earliest layer that a neural network would be able to capture. The middle layers combine the basic features into more complex patterns. So they recognize textures or parts of objects like eyes and noses. And deep layers learn the abstract and semantic features. So for an entire object or for complex visual concepts like a car or a cat, that would be the deep layer. So as I told you that how are we moving on from pixel to edges, like in the form of lines, from lines to, for a straight line, it's easy to represent mathematically if you have an equation y equal to mx plus b. For a curve, however, you would have a quadratic or a cubic equation which would represent a curve. So that level of abstraction requires higher mathematical computation that again gets on added into the same picture. Right? So it's always necessary to understand that the more we move from lines or edges to blobs to anything which is more complex in the form of shape, we are getting into higher form of mathematical calculations also, and that adds more computation to my requirement. That is again going to be there. So these are the features that are learned. So for understanding that yes, this works, we do some pre-processing usually. we would resize the image. As I said, a larger image would be resized to a smaller 224 cross 224 or 96 cross 96 to maintain quality, but we resize the image. Then we may normalize the pixel values to 0 and 1. Then we may do a grayscale conversion from 3 channels to 1 channel. Then we may do a noise reduction for applying blurring to smooth out the noise while preserving features, enhance the contrast, augment the data by increasing same image but from multiple angles, or rotate it, or tilt it. That is that we do. And finally, we do a edge detection at the beginning in the earliest layers. So, canny edge algorithm is something like a pre-processing when we are doing deep neural network. But for our practical purposes, we are looking at canny edge as a practical that we give in the class that kindly identify the edges from this image. And why do we give that edge detection? Because this forms the task of one small minor task of the computer vision algorithm, that in the earliest layers, my computer vision does edge detection. So this edge and how do these edges combine together? And after that combination, it tries to understand the features later in the different layer. So when we give the student the task of edge detection, we also have to tell them that why this edge detection is important for computer vision. Because we can't teach them what happens inside the middle layer and the next layer and the next to next. So that becomes a tricky part. Correct. So I hope that part is understood, that how do we take up the features and edge detection again. So for the feature extraction, we now go into edges and corners. Then we try to find out that whether which features remain same after. If we rotate, does it remain the same? If we scale it up or down, increase the size or decrease the size, does it remain the same? If I change the viewpoint, does it remain the same? So those features which remain invariant with different operations applied to them are the most important to capture, because that is the one which is going to allow us to immediately. Uh, I say why this is important, because I want to be able to recognize a cat. But I don't want to recognize the cat only when it is sitting, standing in the front of me like this. It could be facing me. If it is facing me and I'm still able to recognize, that means there were certain features which were invariant. There were certain features we did not change, even after changing the direction or orientation. Or if I tilt it this way, or if it was standing vertically upside down, for all of these, some features remain the same. They don't change. Those are the features which are the most important, which I need to capture. That becomes the invariant features which we need to capture. Correct. And after that, we keep on doing a lot of things from the edge to shape-based feature. We can do texture analysis. We can do transform-based features, blob detection, color intensity, corner detection, and so forth. All of these are coming into. Okay. The three core tasks that computer vision does, one is image classification. For that, we might even use machine learning, recognizing an object, and object detection in the form of where are they? Where is the dog in this picture, or where is the cycle in this picture? These are some essential requirements that in the increasing order of progression or complexity of these tasks. Okay. And this is the most important task. So my first question was, would we want a high resolution image or a low resolution now? How many of you would say high resolution again? Depends from task to task, but we would, our computer would love to have a lower resolution image if it can solve our purpose. Correct. So what happens? I give you one practical example, that the CCTV camera that we use, yes, depends on requirement. Gajalakshmi perfectly fine. Majority of the task, I might require a high resolution image, but my computer would say, please give me something which is workable. Lower the resolution a little. Let me get it possible to compute. I say, no, no, this low resolution doesn't work. I have to increase the compute a bit. So can you work with this resolution? It says, no, I can't work. I would not be able to compute. Okay, I am lowering the resolution a little more. Can you now work? Okay, yes, I can now work. So CCTV images are usually not colored in captured in color. They are usually captured in black and white. We just want to be able to identify the facial features. We don't need to have the color. So that is the beauty. Or if I am having a thumb impression machine, it might not require to have any more detail than the edges and ridges that are there in that fingerprint. They are the ones which I am looking for. But if I am trying to run a criminal database, I might require to run an algorithm on a high resolution database because I would not want a false positive there. That somebody who is not a criminal, branded as a criminal, that suddenly defeats the entire purpose of running that criminal database. So yes, my computer loves to have a low resolution image, but no, it would not be working with a low resolution image every time. This is where graphical processing unit come. They are processing in parallel all the filters which are running on my image together. So that is the beauty. That image is a grid. That grid has got multiple pixels. All of those pixels can be taken in the form of matrix. And matrices are the one type of data which GPUs are absolutely stunning to work with. So graphical data के लिए even before machine learning came, we were using GPUs. Can somebody tell me where were GPUs used before machine learning? Just put in the chat window. If you have some, ah, Nirender, you must have played a lot of games. Perfect. So the example was, uh, the earliest why NVIDIA was very popular before. Yes, crypto mining again, one perfect example. Crypto mining came in a lot later, but crypto mining was again trying to match input data uh, to an output. That means they were trying to find a hash of a whether the hash would match the data or not. So again, parallel processing, lot of it was working. But yes, before everything else, we were purchasing NVIDIA GPUs when we wanted to play a game. We wanted to make an image transition from this to this to this to this to this, but we wanted it to do it fast. So my matrix multiplication would allow me to see that between one frame to the next, what all transformations are happening that my GPU would be able to do. So my screen would not lag. It would be able to calculate what I require for the next screen immediately from the matrix that I have to what transformation is required. That screen was ready within the GPU before my display would come on it. So that was the perfect example of what computer vision would be applying, that when we are trying to, there we were trying to create the next frame from the current frame and the transformations required. Now what we are doing is we are trying to recognize what is there in my present frame by recognizing the features. So earlier my task was more of generative, but from one frame to the next, how do what changes are there, calculate them, keep the pixels ready for display. Now we want to only learn from the pixel that what is there stored within it. Right. There is the importance of GPU that they can do matrix multiplication very fast. Okay. Now for convolution, we will go to something in the form of CNN. And this, okay, I would share this with you on your chat window so that you can use it later. Okay. So I spoke about object detection and object classification. See, there are two terminologies. When I am talking about object detection here, this is simply trying to create a bounding box. Object classification and image classification are two different things. One, first I talk about image classification. Image classification is easy, that we might want to separate one image from the other. object. Then comes in object recognition. That yes, are there multiple objects within this image? I don't want to localize them yet, but I would be able to say that is there a cat in this picture? Yes, there is. Or is there a castle in this screen? Can somebody tell me, is there a castle in this screen? That part is identifying. Okay. So I can recognize yet that there is a castle in this screen. But when I put a bounding box here, that basically is object detection. If I create a boundary around this, that this is where the castle is within that image. So that part is a harder part. But if I just have to classify between a cat and a dog, that image classification was a easier task. So I wouldn't use object classification and image classification as the same. I would use them differently. Does that answer your question, Virender? Okay. So let's go ahead and take this visualization now. Let me reduce the size. Okay. So this is a visualization. I'm going to hide all the layers first, even the convolution layer. So let us say we draw a figure of 8 here. You see, this is how it would be looking in the form of a grid of pixels. Okay. I could have erased it, some part, right? I can create a different image here. Let us say 6. Okay. Now there is a downsample drawing. Let us add a convolution layer here. My convolution layer had what job? It would try to identify the basic features in my image. That where are the edges located? So how does it captures? See, the first corner pixel with the convolution is a summary of all the this complete block. So from this block, it got this much information. From the second, from the third. So when I reach this set of block, you see that it is capturing the information from the input image and the filter, both are shown. Okay. For this empty region, the input image is black, completely dark. The filter is the same, but now it sees the output as some value. But for a brighter pixel, because it is now capturing an area where there are some image which is bright, some image which is dark. So there is still something that we have available. So it would have a higher calculation here. So this keeps on going for all of these. So see, when I move this is how the convolution happens. So it is layer by layer, but we are now trying to capture the details in each part of the image one by one. Right? But the filters are different. So for this image, the filters might be different. See, the previous image I had a different filter. The second had a different filter. The third had a different filter. The fourth had a different filter. Why we apply so many filters? Because I may want one filter to be able to capture the straight edges, one filter to be able to capture the horizontal edges, one filter to be able to capture the slanting edges. So we would create different filters to capture different information in the image. So if I have to identify a 7, I should be able to identify this also. I should be able to identify this also because both of them make a 7. So that is how my filters would be. But for recognizing from 0 to 9, I would have to have identify a lot of different edges and classify them against each other. Right. So second is a downsampling layer where I try to now apply a max pooling or something that I don't want all the pixels here. Can you club these 4 pixels together into one so that I have a little lower resolution image because my computer doesn't like a very hard amount of data. So let us downsample it a little. Then apply another convolution. Let me try to capture what am I getting from multiple parts here, right? Where are the features located which are bright? Where are the features located which are dark? Let me capture this information. Then comes again another desampling that we want to reduce the lower. Then comes a fully connected layer which captures information from all of them. Another fully connected layer. And finally, there is the output layer which is capturing data from all of these together and identify that the first guess is a 6. What if I had a 7? See, the process repeats again. That downsampling, then convolutional, then downsampling. So this is why we are putting in layers, then max pooling, then another layer, then max pooling, and so forth. Okay, this part was the easiest when what computer vision deals with. Then comes in segment anything by meta. So I am sharing this. Okay, that would work. See, this is the beauty of computer vision. If you cut the 7 in the middle with a horizontal line, if it has learned from enough number of people cutting 7 with a middle line, it would be able to recognize it. But if you are the only one who cuts 7 with a middle line, then it becomes tricky. It would say, yes, I feel 70% that it's a 7, but I don't recognize this line. That's so that I am not confidently 100% sure this is a 7. It could have been 3 by mistake. So somebody wrote 3 incorrectly. So there is a 30% chance this is a 3. But if there was no middle line and entire data it saw was no middle line, then it might clearly identify 7 with a 95% accuracy. That works. So the next we are looking at is how do we do segmentation. We will see a small demo of this. So for this image, what it is doing is when you are hovering over it, it can identify different regions by the how the pixels are related to each other. Let us try to segment everything.
कोई कहता पीछे रखो मेरा वो चढ़ रहा है आपका बहुत ज्यादा
Come again. So here is it that which identifiable parts could I manage within that image, putting them into a box also, separating them from the remaining portion also. I may try to cut this out, right? Let me go over and click on this, and within that also, so cut out this object. Then how could my computer understand that this is different from the other? And it could cut this out specifically because the pixels within this are more closely related to each other. So when I have to create a bounding box around something, so where did that go? I mean, we had a very, so if we need to understand there is a castle, thank you Karishma for the example that I can see on my screen. So if there was a castle that I needed to work with, then where is this castle within this image has to be clearly because they have similar intensity of the color pixels. Where this tree has got a different color intensity, the sky has got a different color intensity. So this is how we try to capture information within the image. So if we can, if we want, we can cut out a single tree or multiple or the complete forest or the entire grass. This is what my segmentation algorithm is learning. This is even harder than the first part that we wanted to work with. Correct? So this is how computer vision works. I have included all of these source codes in the class 10 book also. In the class 12 book also, every example that you would require, there is a source code available as a part of the book. That how do we extract a region, how do we convert from uh, color to a grayscale image. And in fact, we have also added the code for more examples which can be used in the project as well. Even for localization, yes, you would image localization basically is a logical requirement for segmenting. Unless and until you localize something, you will not be able to segment it. So localization is bounding by a box, but after binding it, if we want to say there are multiple cats, after that, after you classify that object or understand that object, the next step would be where are they in the images. If there are multiple, then segmentation is the next logical step that let us separate them out. So that becomes the third part. I hope that answers your question, Vijay Lakshmi. Perfect. So I think that's my time. We have taken a lot of time for a lot of data today. Any more questions? I'm open to them before we close this session. Any question from the audience? If there are none, thank you so much. Ashish sir, anything at the YouTube?
None, sir.
Thank you. Thank you so much. Okay, PPT I will share with all of you. It's on the AI for teachers group. We will share the PPT. Manmohan sir, we can close. Thank you so much.
Yes. Another grossing session, Dr. Gupta. Thank you so very much. And thank you all the participants. Hope you enjoyed the session. Another webinar is on the way. Do tune in and have a great weekend.